Hi guys, let's see here. We're on Unit 8, Lesson 9, Linear versus Exponential Sequences. Algebra is torture, but the whole first section of this lesson is review, so it should be easier. Arithmetic sequences have linear change and can be modeled with linear functions. Geometric sequences have exponential change and can be modeled with exponential functions. Linear functions are straight lines with the formula f of x is equal to mx plus b, and exponential functions are curved lines with the formula f of x is equal to a times b raised to the power of x. So how far does the linear function f of x equal to x grow? For an interval of width 1 between values of x, what is the difference in the values of x? And for an interval of width 2 between values of x, what is the difference in the values of f of x? We're going to do this together. We're going to make a table, and here are our points for a width of 1. You can see that in the x column where we're going up by values of 1, 0, 1, 2, 3, 4. So if you plug in those values for x into our formula, f of x is equal to 2x, and then solve the problem, you end up with 0, 2, 4, 6, 8. Then if you take our values for f of x and subtract the second number from the first, so subtract 2 from 0, you get 2. 4 subtract 2 is 2. 6 subtract 4 is 2. And 8 subtract 6 is 2. That means that the rate of change is steady, and it is 2. So for the formula f of x is equal to 2x, when x equals 1, or over here, our f of x is going to be equal to 2. When f of x is equal to 2, okay, so we have 0, 2, 4, 6 when x is 2. Then we have 0, 4, 8, and 12. Then we go 4 minus 0 is 4, 8 minus 4 is 4, 12 minus 8 is 4, our rate of change is 4. So when x equals 2, f of x equals 4. So for both of these problems, the rate of change was the same. They're both linear, but they have different rates of change. This one is steeper than this one. Okay. Let's talk about linear functions. Linear functions grow by equal differences over equal intervals. That's why they appear as straight lines. How does the exponential function f of x equals 1/3 times 4 raised to the power of x grow? For an interval of width 1 between values of x, what is the growth factor between the values of f of x? So we looked at what happens with a linear function. Let's look at this exponential function. Okay, so we have x is equal to 1, 0, 1, 2, 3. Okay, so if we take these, plug them in for the values of x up here, we get 1/3, 4/3, 16/3, and 64/3. And then, because we're dealing with an exponential function, we're not subtracting anymore. We're doing 4/3 divided by 1/3 gives us a rate of change of 4. 16/3 divided by 4/3 is 4. 64/3 divided by 16/3 is also 4. So our rate of change here is 4. Exponential functions can show growth or exponential decay. The function f of x equals 1/3 times 4 raised to the power of x grows by factors of 4 over intervals of width equal to 1. That's what we just did. Model f of x is equal to 1/3 times 4 raised to the power of x with a table to show that it grows by factors of 16 over intervals of width equal to 2. So now we're going to have x equal to 2. How does the growth factor of 16 relate to the base of the function f of x is equal to 1/3 times 4 raised to the power of x? That's a really long, complicated way of saying what happens when x equals 2. Okay, so when x equals 2, we're going 0, 2, 4, 6. Okay, plug these values into this formula and solve. You get 1/3, 16/3, 256/3, 4096 over 3. Okay, so you can see these numbers jump much higher. The first number is the same, 1/3, and then it just goes vroom, real fast. Okay, so the growth factor, you're going to take 16/3 and divide it by 1/3, you get 16. This is that growth rate they were talking about. When the growth rate is 16, what happens to your line? it goes fring, right? It makes that curved line and it starts accelerating really fast. It's not straight. It's not pretty like that. It starts going curved and getting vertical really fast. Consider the function f of x is equal to negative 4.29x times, plus 3/5. If the interval between consecutive x values is equal to 1, then how are the consecutive f of x values related? Explain your answer both in terms of slope and with a table. This one has a picture, so this one's yours. So all you're going to do is take x values equal to 1, so like 0, 1, 2, 3, 4, plug those in here, make a nice little table, and then figure out what the slope is. Pause the video, do that, come back. So here's our table. They did 0, 1, 2. Okay. So if you plug 0 in for x in this formula, you get 0.6. For 1, you get negative 3.69, and for 2, you get negative 7.98. To find the slope, take the second number, subtract the first number, because we're not dealing with any exponents here, we're dealing with addition and subtraction. So negative 3.69 minus 0.6 is equal to negative 4.29. And then negative 7.98 minus a negative 3.69. When you have minus a negative, it becomes plus, add, is negative 4.29. We have a steady rate of change of negative 4.29. Okay. Here's practice question 1 at the end of your lesson. This table represents the growth factor of the function f of x over equal intervals. What could the table be used to prove? Okay, so we've got this table, we've got our x values, and then we've got our f of x values, and then we've got our growth factor. And you'll be able to read this a lot easier on your practice questions. I had to crunch a whole bunch of information into this little teeny tiny table. Okay, so on this page we have our table again, and these are the options it gives you. What can you prove with this table? Over equal intervals, linear functions grow by equal differences. Over equal intervals, linear functions grow by equal factors. Over equal intervals, exponential functions grow by equal differences. Over equal intervals, exponential functions grow by equal factors. Okay, so the first thing we need to figure out is this a linear or an exponential function? So looking at all of this, okay, we've got this exponent, that means it's exponential. So 1 and 2 are out. It has to be either 3 or 4. Okay, now do exponential functions grow by equal differences or equal factors? Differences mean addition and subtraction. Factors mean multiplication and division. Well, if you look right here, it's doing division, so it has to be number 4. Here's quick check question number 1 at the end of your lesson. It says Ramona wants to use the table to prove something about how exponential functions grow. What does she need to do next, and what will she be able to prove? So here's our table. We need to look at that. We need to figure out what she needs to do next, okay? And then what she'll be able to prove. And here's your options. So the next thing she needs to do is subtract the x values from the f of x values. Okay, so subtract these from this. Does she need to add another column to the table and find the growth factors between the consecutive values of f of x? So does she need to add a table here and find the growth values between like this term and this term, this term and this term? Okay. Does she need to subtract the x values from the f of x values? So does she need to subtract this from this? Or does she need to add another column to the table to find the change in f of x values? So does she need to add another table column over here to find the change in here? Okay, so those are your 4 choices for what she needs to do next, and then you need to figure out what she can prove based on that next step. I'm not going to do it for you. Okay. Consider I had all of these so that they all matched, but something went wonky. I apologize. Consider the linear function f of x is equal to 2.5x, and the exponential function g of x is equal to 2.75x. Use sequences to calculate the rates of change of each function. How does the growth rate of f of x compare to the growth rate of g of x? How do the terms of the sequences compare? So we have a linear function and an exponential function right here, and we're going to look at how they compare. Right? So I couldn't take it. I had to change it back to black. Okay, so here's our table of information. What we know is that by the third term, so right here, g of x has a growth rate that exceeds the growth rate of f of x. Okay, so the growth rate here every time is, okay, so it's steady for linear sequences. So the growth rate every time is 2.75 here. Okay, so the change here would be 7.563 minus 2.75. So the change here is 4.813. Okay. The change here is going to be huge because you can see it's 20 minus 7. So by here, the growth rate has exceeded the growth rate of this one. Okay. The two sequences have the same first term. They're both 2.75. But by the second term, g of x is greater than f of x, and the difference between the sequences keeps expanding. Okay, so here they're the same. The two lines would match on a graph, but here this one's bigger, and the gap just keeps getting bigger and bigger between the two. Okay, can you see that? Consider the linear function f of x equals 2,000 times x, and the exponential function g of x equals 1.2 raised to the power of x. Use sequences to calculate the rates of change of each function. How does the growth rate of f of x compare to the growth rate of g of x? How do the terms of the sequences compare? So we're doing the same thing again. We're going to make a table with all of this information. Okay, it provides it for us. You don't have to sit there and make a table with 65 points on it. But the sequence for f of x, you can see it goes 2,000, 4,000, 6,000. Every time it's increasing by 2,000. 102 to 104, 128 to 130. Okay. This exponential sequence is going from 1.2 to 1.44 to 1.728. When you get into the bigger numbers, it goes from 10,000 to 13,000 and from 116,000 to 140,000. You can see that the gap is getting bigger and bigger and bigger on the exponential sequence. So by term 52, the growth rate of g of x exceeds the growth rate of f of x. Okay, so here you can see that it's at 104 and the growth rate is 2,000. Here it's more than 2,000. It's going from 10,000 to 13,000. The exact amount is, sorry, I have to keep pulling up my computer calculator. I don't know where my physical one is. But 104,000 minus 13,105 is 90,008. I'm doing this wrong. Let me figure this out. How? Oh, it's because it's between the two. So it's 13,105 minus 10,921. Okay, so the difference here is 2,184. This is 2,000. So right here, this one starts to win. This one's getting bigger faster. Okay. While f of x started out with terms that were much greater, here 2,000 is way bigger than 1.2. By 65, by the 65th term, g of x is greater than f of x. Here, this one's bigger than here. The 140 is bigger than 130. Here, this one's still smaller, and this one's bigger. But by here, this one's bigger, this one's smaller. Okay? This whole lesson's just about learning to read these tables and figure out where the growth rate flips and where the value, the actual number, is bigger and smaller. And look at that. I'm sure I had something here and it got screwed up because my life is a gift. All right. This was supposed to pause. This is going to be a very rough video. I'm sorry. Suppose you won a unique prize where you would receive money every day for 30 days. Which of the following options would you choose? Option number 1 is $1,000 on day 1, $1,000 on day 2, $2,000 on day 2, $3,000 on day 3, adding another $1,000 each day until day 30. Option number 2 is 1 cent on day 1, 2 cents on day 2, 4 cents on day 3, doubling every day until day 30. So first, use sequences to calculate the rates of change of each function. Second, how does the growth rate of f of x compare to the growth rate of g of x? Third, which option for 30 days of money would you choose? And fourth, what if the prize were for only 20 days instead of 30 days? Would that change your answer? So first, option number 1 is an arithmetic sequence, and it grows equally over equal intervals, so it's a straight line. And option number 2 is a geometric sequence that grows exponentially. Oh my goodness, this whole thing is just so screwed up. Let me see if I can fix it. Okay, hopefully that didn't just screw up my whole thing even more. Okay, so and there's supposed to be formulas here. I apologize. This is f of x. It goes 1,000, 2,000, 3,000, and then on the 18th, for the 18th number, it's 18,000, 19,000, okay? I ran out of space over here. It goes clear off the screen, so for day 30, day 30, it's 30,000 and 5 million, okay? So if you look at these two, okay, we can obviously see that it's better to take the one that starts out at 1 penny because you end up with $5 million. And if you take the one that starts out at 1,000, you only get $30,000. I'd definitely rather have 5 million. So the sequence for f of x consistently grows by 1,000. So the rate of change for f of x is 1,000. The sequence for g of x does not grow by a consistent number. Its rate of change keeps increasing. By term 19, the growth rate of g of x exceeds the growth rate of f of x. So here, the change is $1,000, and here it's more than $1,000 because you can see it's 1,300 and it's 26. Okay. Come back over. While f of x started out with terms that were much greater than the terms of g of x, by the end of 30 days, you would receive millions of dollars more each day with option number 2 compared to option number 1. By day 19, option number 2 is growing at a faster rate than option number 1. However, at this point, the value of option number 2 is $2,621.44, which is less than the value of option number 1, which is $19,000. So let's go look at day 19. So you can see right here, if you stopped at day 19, even though this one is going to end up on day 30 with a huge amount, if you stopped at day 19, it would make more sense to take the first option because you'd get $19,000 instead of $2,000. Similarly, on day 20, the value of option number 2 is $5,242.88, which is less than the value of option 1, which is $20,000. So by the same standard, if you stop on day 20, you're better off with option 1 than you are with option 2. Okay? So it depends on where you're looking at in the sequence, which option is better. Just because a function has a greater growth rate at a particular point in time does not mean that it will also have a greater value at that point in time. It will eventually have a greater value, but in this case, not in the first 20 days. Okay, your turn. Use sequences to compare the growth rate of f of x is equal to 50x plus 100 to the growth rate of g of x is equal to 10x plus 3 raised to the power of x. There, it's a little bit easier for you to read. Go ahead and pause the video, solve that, come back. Once again, it's screwed up, sorry. This was the first, this was the second. So here is your first formula, here's your second formula. F of x always comes first, g of x is second. So this is what your table is going to look like, and what you need to pick apart from this table is that by term 2, the growth rate of g of x exceeds the growth rate of f of x. So here it's growing by 50s, here it's growing by 60. So right here, this one is growing faster, okay? But it's not worth more in money until 4, okay? This one's all you. A new bank is offering a special promotion for new savings accounts being opened with $500 deposits. The promotion offers 2 options for how to earn interest on the $500 deposit. With the first option, the account will earn $50 each year in interest. I'm yawning because this is so interesting. The function f of x is equal to 50x plus 500. Describes the amount of money in the account after x years with the first option. With the second option, the account will earn 5% each year in interest. The function g of x is equal to 500 times 1.05 raised to the power of x describes the amount of money in the account after x years with the second option. Use sequences to compare the growth rates of the 2 accounts. Note that this is a simplified situation where no additional deposits are made and no money is withdrawn from the account. So pause the video, figure it out, come back. Here's what your table is going to look like. And you can see that the growth rate of f of x stays constant at 50 through the whole thing. This is just adding 50 every time, okay? While the growth rate of g of x is always increasing. So here it went up by 25. Here it went up by, 26.25. It's getting bigger every time, which is what you're going to see every time. Linear goes up by the same amount. The growth rate is getting bigger every single time. Okay, practice question number 2. Miguel is planning to invest $5,000. He plans to withdraw his investment and earnings in approximately 10 years. With option number 1, his money will grow according to the function p of x is equal to 5,000 times 1.06 raised to the power of x. With option number 2, his money will grow according to the function q of x equals 500x plus 5,000. He creates sequences for both functions. Which option has the greater rate of change between years 9 and 10? Which option should he choose for his money? So this one, they flipped it. The linear equation is on the bottom and the geometric is on the top. So that's the only thing to watch, okay? So they want to know between years 9 and 10, who has the greater rate of change, okay? So I got to get my calculator out again. Okay, let's see. Rate of change. So we have 8954.2 minus 8447.4. So the top one is 506.8, and you can see that the bottom one is just 500. So option number 1 has the greater rate of change between years 9 and 10. And because he's going to leave it in there for 10 years, he should choose option number 1 because he's going to get a whole whopping $6.80 more money. Yay, Miguel, look at you. Option number 1 has the greater rate of change between years 9 and 10. If Miguel plans to invest his money for only 10 years, he should choose option number 1. Wow, Miguel. Okay, quick check. Question 2. Actually, it makes more sense to take option number 2 because he's going to get 500 every time. And this one is going to be less every time. This is where it switches. And this one becomes a better option. But he probably should take number 2. Yeah. The greater rate of change is option 1. But he should probably take option 2 because he's going to get 500 every time. And like here, he's not getting 500. Here, he's not getting 500. So he should probably take option 2. Okay, quick check question number 2. Here's your table. Which statement correctly compares the two functions? By term 12, j of k is greater than h of x. The growth rate of h of k is always less than the growth rate of j of x. The average growth rate of j of k exceeds the growth rate of h of x between terms 11 and 12. The values of j of x are always less than the values of h of x. So go ahead and figure that out. Figure out which one of these is right. Moving on, consider the linear function f of x equals 2x and the exponential function g of x equals 2 raised to the power of x. Model these functions with graphs. How does the growth rate of f of x compare to the growth rate of g of x? Now, just so you know, you don't need to actually know how to put these into graphs. It's always going to provide you with the graphs for all of your questions, for all of your testing. So you can go to geogebra.org and make a graph, but you don't need to because it's always going to provide you with it. Okay, here's our beautiful little graph. It has both of our linear line and our geometric line on the same graph so we can see how they compare. What this tells us is on the left side of the graph, g of x is greater than f of x. You can see that clearly, but is growing at a slower rate. You can see it's almost level over here. It's not growing very fast. Okay, this is growing pretty dang fast over here. You can tell this because g of x is less steep than f of x when x is less than 1. Okay, so everything to the left of here, this one's growing slower, this one's growing faster, this one's worth more, this one's worth less. Okay, between about x equals 1 and about x equals 2, the graphs appear similar. So here and here, they're very close to each other. The steepness of their curves is similar, and therefore their growth rates are similar over this interval. The growth rate of g of x looks like it starts to surpass the growth rate of f of x by the end of this interval. So g of x is this orangey brown line, and it looks like at the end of this interval it's going to win. It's going to start growing faster than the blue line. After x equals 2, so after this point where they cross again, g of x is greater than f of x. Orange is better than blue, and now also has a greater growth rate than f of x. You can tell this because g of x is steeper than f of x when x is greater than 2. The growth rate of f of x stays constant, while the growth rate of g of x always increases. For small values, the graph of g of x is less steep, so this orange one, it's less steep, than the graph of f of x, so the growth rate of g of x is less than the growth rate of f of x. Over time, g of x becomes steeper and steeper. By x equals 2, the growth rate of g of x exceeds the growth rate of f of x. And this is what you're going to see every time, okay? As long as g of x is not a decay function. The growth rate of an exponential function will always eventually surpass the growth rate of a linear function. Always. Eventually, this one is always going to beat out your straight line. Consider the linear function f of x equals 2000x, and the exponential function g of x is equal to 1.2 raised to the power of x. Model these functions with graphs. How does the growth rate of f of x compare to the growth rate of g of x? So the last one we looked at, they were both 2, okay? This time, we're looking at when they have a huge starting difference, 2000 and 1.2, okay? On the left side of the graph, g of x is greater than f of x. So over here, our exponential one is greater than f of x, but is growing much more slowly. Around x equals 50, the growth rate of g of x really starts to increase. So it looks like it's not even growing. It is if you zoomed in, but it looks like it's not until about here. And then it's like, ring! The growth rate of g of x really starts to increase. Soon, by x equals 55, so about halfway through here, g of x is steeper than f of x. This is definitely steeper than our blue line. And thus, g of x is growing faster than f of x. When x is greater than 64, so about here-ish, g of x is greater than f of x and is growing much more quickly. The growth rate of f of x stays constant while the growth rate of g of x always increases. For small values of x, the graph of g of x is less steep than the graph of f of x, so the growth rate of g of x is less than the growth rate of f of x. Over time, the growth rate of g of x exceeds the growth rate of f of x. A new bank has just opened in Carlos's and Michelle's city. The bank offers a special promotion for new savings accounts opened with a $500 deposit. The promotion offers 2 options for how to earn interest on the $500 deposit. With the first option, the account will earn $50 each year in interest. The function f of x equals 50x plus 500 describes the amount of money in the account after x years with the first option. With the second option, the account will earn 5% each year in interest. The function g of x equals 500 times 1.05 raised to the power of x describes the amount of money in the account after x years with the second option. Note that this is a simplified situation in which no additional deposits are made and no money is withdrawn from the account. Both Carlos and Michelle plan to open new savings accounts at the bank, but neither is sure which option to choose. Carlos plans to leave the money in the account for 5 years, at which point he will withdraw the money to use as a down payment on a car. Michelle plans to leave the money in the account long term and maybe use it in her retirement in 40 plus years. Which option should Carlos choose? Which option should Michelle choose? We've done enough of these by now that even my non-math brain was able to click and say, well, if you're going to do short term, you're better off with the linear function. If you're going to do long term, you're better off with the exponential. So I don't know if your brain has gotten there yet, but they're going to go through all of the complications to prove this. The first option is a linear function, while the second option is an exponential function. At first, the linear function grows faster than the exponential function. However, the growth rate of the exponential function keeps increasing. From about x equals 14, so right about here, to x equals 16, right about here, it appears that the growth rates of the two functions are very similar. Eventually, after about x equals 15, right about here, the growth rate of the exponential function exceeds the growth rate of the linear function. Between 26 and 28 years, right in here, the two functions intersect. At this point, the amount of money in the first option is equal to that in the second option account. After the intersection point, the amount of money in the second option account exceeds that in the first option account. So this intersection point is the point where if you hit that exact point, it doesn't matter which one you use, but anything after this, you're better with the exponential one. You're going to make more money. Carlos plans to leave the money in the account for 5 years, which is right here. So he should choose the first option because the orange line is higher. Michelle plans to leave the money in the account for 40 years or more. So she should choose the second option, which is the blue line, the exponential one, because it is higher, which is what I said at the beginning, but okay. This one is all you. Use graphs to compare the growth rate of f of x is equal to 50x plus 100 to the growth rate of g of x is equal to 10 times 5 raised to the power of x. Go ahead and pause this video, come back with your answer. So the graph shows that while f of x has the greater growth rate, it goes whoop, whoop, whoop. Okay, this one. The growth rate of g of x eventually surpasses it. Okay. This one is steady at the beginning, this one it does better, and then this one surpasses it just like it does always when both are growing. A farming community has decided to purchase ducks to keep on their land. I have ducks. They are planning to sell the ducks' eggs in their farm store. My ducks are boys. I do not have duck eggs. They assume that the number of ducks they have each year will grow exponentially according to the function f of x is equal to 5 times 2 raised to the power of x. To account for the new ducks, they plan to purchase food to feed an additional 10 ducks each year. The number of ducks that they will be able to feed each year is given by the function g of x is equal to 10x plus 10. What is wrong with the farm's plan? Use a graph to support your answer. This one is all you. Pause the video, solve it, come back. Before we even start, I can tell you right now what's wrong with their plan. They have an exponential formula and then they're increasing their food linearly. Wrong. And there you can see the problem. The graph shows that the farm will be okay for the first 3 years. They're going to have more food than they need. During these years, the amount of food they have is greater than the amount of food they need for their ducks. But after 3 years, they won't have enough food for all their ducks. The growth rate of the number of ducks quickly surpasses the growth rate of their food supply. And by the way, another thing they didn't take into consideration is that all of the birds love to eat the duck food. So you have to take into account that you're feeding the wild bird population. Here is practice question number 3. Consider the graph of function number 1, which is linear, and function number 2, which is exponential. How do the growth rates of the two functions compare? Initially, function blank has the greater growth rate by x equals 8, which is right here. Whoop. The growth rate of function number blank surpasses the growth rate of the function. And guess what? It's not at x equals 8. They lied. Where it changes is about x equals 11.5. This book is amazing. So initially, function number 1 has the greater growth rate. And then by like x equals 11, not number x equals 8. Then function number 2 takes over the growth rate. It's where they intersect. Way to go, book! Practice question number 4. Given that the graph f of x is linear and the graph g of x is exponential, solve the following problem. The graph of f of x and g of x is shown. Which of the following statements is true? The growth rate of f of x, which is our blue line, is greater than the growth rate of g of x between x equals 0 and x equals 30, while the growth rate of f of x is initially greater than the growth rate of g of x. The growth rate of g of x keeps increasing, and by x equals 23, which is right about here, surpasses the growth rate of f of x. So where do they switch? It's number 1. It's at about 30, where they intersect right there. While the growth rate of g of x is initially greater than the growth rate of f of x, which is never true, this isn't initially greater, the growth rate of f of x keeps increasing and by x equals 30 surpasses the growth rate of g of x. So it's still what I said. Practice question number 5. Oh, look how screwed up this got. It's got our, oh my gosh, it's got our function in the wrong place. Wow, okay, yay. Given that the graph q of x is linear, so q is blue, and the graph p of x is exponential, p is orange. I'm a grown-up. Solve the following problem. Juan is planning to invest $5,000. With option 1, his money will grow according to the function. Oh, option 1. Okay, option 1 is the curve. 5,000 times 106 raised to the power of x. With option 2, his money will grow according to the function q of x is equal to 500x plus 5,000. He decides to graph both functions. What does he observe from the graph? For the first 10 years, Juan's money, so here's 10, will grow faster with blue, which is q of x, which is option number 2. Okay. But after that, it will grow faster, and it's not at 10. They're so silly. Oh my goodness, it's at 16. Oh my word. Okay. But at 16, it will grow faster with option 1, which is our orange P. Quick check question number 3. Austin is using the graphs to compare the growth rates of g of x equals 1.3x and f of x is equal to 1.3 raised to the power of x. Which statement is true? The growth rate of f of x, which is our curved line, okay, here's f of x, it's orange, is less than the growth rate of g of x until x is approximately 2.7. 2.7 is right about here. The growth rate of f of x is greater than the growth rate of g of x when x is greater than approximately 2.2, which is right there. And then there's more options. The growth rate of g of x is only greater than the growth rate of f of x when x is between 1 and approximately 27. It's probably supposed to be 2.7 and I probably screwed it up. The growth rate of f of x is greater than the growth of g of x when x is less than 1. Okay, figure out which one is correct for that one. Quick check question number 4. Given that the graph f of x is linear, and the graph g of x is exponential, solve the following problem. Consider the graph of function number 1 and function number 2. How do the growth rates of the two functions compare? Initially, function number 2 has the greater growth rate. After x equals 32, which is right about here, the growth rate of function number 1 surpasses the growth rate of function number 2. Second choice, the growth rate of function number 2 is always greater than the growth rate of function number 1. Option 3, the growth rate of function number 1 is always greater than the growth rate of function number 2. And option number 4, initially function number 1 has the greater growth rate. After x equals 32, which is right about here, the growth rate of function number 2 surpasses the growth rate of function number 1. Again, 32 is not an option. I'm guessing they meant like 46. This book. All right. Quick check question number 5. Marshall is comparing the growth rates of f of x equals 6 times 1.5 raised to the power of x, and g of x is equal to 5x plus 10, using this graph. Based on the graph, he concludes that the growth rate of g of x is always greater than the growth rate of f of x. Where is his mistake? Marshall has it backwards. The growth rate of f of x is always greater than the growth rate of g of x. That's option 1. Option 2, Marshall is only considering a small portion of the domains of the functions. If he went farther to the right, so farther over here on the graph, he would observe that the growth rate of f of x eventually surpasses the growth rate of g of x for large values of x. Option number 3, Marshall is only considering a small portion of the domains of the functions. If he went farther to the left on the graph, so farther over here, he would observe that the growth rate of f of x eventually surpasses the growth rate of g of x for negative values of x. And the last option is the growth rate of g of x is only greater than the growth rate of f of x when x is greater than approximately negative 1.3, which is right about there. Remember, the order my answers are in will not match the order your answers are in. And guys, it's finally December, which means the first semester of algebra is so close to being over. Yay!